Swayam Prabha. Digital India. Educated India.
Hello and welcome to another lecture of this course Mathematics for Economics Part 1. So today we are going to start with a new module, and this module is the last module of this course. The name of the module is Difference Equations. The difference equations, this particular module is a little bit different from what we have been discussing so far. The last topic that we have covered was integration, and before that we were taking the optimization exercise as the subject of the module. Now, difference equation is a little bit different from all these topics in the sense that now we are talking about time and how the variables change with respect to time, right? So, our focus will be solely on time. Time is the independent variable, and we are trying to see how the variable of interest of us, for example, the price level or the GDP of a country or the output produced by a firm, they change with respect to time. So, that is a sort of dynamic analysis that we are going to introduce from this module, and we are talking about difference equations. So, we are going to discuss what it means when we say difference equations. So, this is the title slide, as you can see. Time, since we are talking about time, t, now this t can be primarily seen in two ways, either as a continuous variable or as a discrete variable. So, if you are taking time as a continuous variable, then it means t can take any possible real value within any interval. Suppose 0 to 1 is the interval, then t can take any possible value within 0 and 1. But we are talking about discrete time. So, in the latter case, that is the discrete time, t takes only discrete values. It could be a year, a month, a quarter, etc. The variable of interest which changes with time can be represented. So, this is can be represented by small y. Now, what is small y? This variable of interest, it could be the GDP of a country, the national income of a country, let us suppose. So, that is suppose y, and this y changes with respect to time. Or it could be GDP of a country, but this GDP could be measured in different ways. It could be on an annual basis, right? Generally, that is the idea of GDP one has, that this is the textbook definition of GDP, that we are measuring the output produced within a country, the final value of goods and services produced within a country in a year. So, when we are saying in a year, that means we are taking the GDP on an annual basis. Maybe a calendar year, let us say 2020, that is a calendar year, or it could be a financial year. So, for example, in India, the calendar year and the financial years are not the same. In India, the financial year starts from April and it ends in March. So, that is the financial year, and as you can see, it does not actually coincide with the calendar year, which is from January to December. But GDP can also be measured not in an annual basis, but on a quarterly basis. Quarterly basis means every 3 months, right? So, you divide the 12 months into 4 parts, that is why it is called quarterly. So, if you divide the entire year into 4 parts, then each part will consist of 3 months. And so, what we do in this case is that we look at the total value of goods and services, final goods and services produced in a country in a 3-month period. So, that will be like the quarterly GDP. Okay. So, it could be like in Indian case, the first quarter will be April to June, April, May, June. So, that is a quarter, the first quarter. Then there will be second quarter or Q2. Likewise, there will be 4 quarters. But whatever it is, we are talking about a period of time, right? In this case, time is not a continuous variable. It can be divided into small irreducible periods. It could be a quarter, right? If we are talking about quarterly GDP, or it could be annual GDP. So, one does not talk about, for example, GDP of a second, right? That is absurd. So, that basically means that here the GDP that we are talking about is measured with respect to time, but that time is discrete time. In this module, we are going to consider time in discrete units and analyze how, why not necessarily equal to GDP, it could be some other variable, for example, prices, how y changes with time, and it is a dynamic analysis because we are looking at the behavior of a variable with respect to time. Since time is discrete, the values it takes are called periods, right? They are not points of time, they are not points, but they are periods of time. So, t, that is time, can take these values, whole numbers 0, 1, 2, 3 like that, and each of these is called a period. Thus, the discrete version of economic analysis is also called period analysis, right? Since we are talking about periods, not points, and therefore, the analysis that we are going to carry out, the economic analysis, will be called period analysis. Now, as time changes from one period to the next, the change is denoted by this notation, delta t, right? Delta means change. So, delta t is the change in time. In particular, what is important here is that we are implying that the time is changing in a discrete manner. Correspondingly, the variable of interest y also changes, and that change, let us suppose that is given by delta y, right, to maintain consistency. Since change in time is denoted by delta t, the change in, let us suppose, the GDP is also denoted by delta y. Now, we can look at the ratio of these two. Ratio of these two means delta y divided by delta t. Okay, so, what does it mean? It means the change in the variable of interest, that is, let us suppose GDP, with respect to 1 unit change in the time, and this is called the difference quotient delta y divided by delta t, which turns out to be only delta y, since the smallest change in t is 1. Okay. So, if delta t is by that we mean the smallest possible change in time, and we know time is discrete, and so the minimum possible change that can take place in time is 1, right. So, delta t is equal to 1. So, delta y by delta t boils down to delta y, because here by delta t I mean the smallest change that is possible, because time changes from one period to the next is equal to 1. So, delta y by delta t is same as delta y. Delta y is called the first difference of y. The expression delta y is ambiguous, since depending on the value of t, one can have different values of delta y. Okay. You know, think about this. So, suppose this is how y is changing, y, and here you have time. Now, if you take this change in t, so this is delta t, which is equal to 1, then here you can see the change in y is very small. Whereas, if you take the same change in time here, the change in the variable is quite large compared to here. So, delta y is an ambiguous expression. It can change depending on what t we are considering, right? What is our reference t? So, to get around this problem of what is the value of delta y in a very concrete manner, we use the subscript small t, okay, and that denotes the period of t. So, what is the reference point? Are we talking about this t, right? This could be t1, or are we talking about this t, which is t2? So, to denote the t that we have in mind, we use this small subscript here. So, y subscript t. So, that will give us the reference point of time. Sometimes it is also denoted by yt. So, instead of writing this, we can also write y which is dependent on t. Both of these things mean the same. Now, delta y may mean y1 minus y0, or it can mean y10 minus y9 as well. In both cases, time is changing by just 1 unit, and we are looking at how much the y variable is changing. But as you can see, how much y variable is changing might be quite different depending on what original t or the reference t we are considering. Here the reference t was 0, here the reference t is 9. So, as you can see in the picture that I have drawn, depending on whether t is 9 or t is 0, these values might be quite different. Okay. So, this is the thing that we use, that delta t. What is meant by delta t? Delta t is equal to yt plus 1 minus yt. So, the change in time is taking place by 1 unit. With respect to that, the change in y is taking place, right? But from what t time is changing, here that is denoted by this small subscript. So, in case of if we take this bracket expression, it will be like this, right. So, that will be delta y t, okay, had we used the bracket expression. But in this module, at least, we are not going to use the brackets, we are going to use the subscript. Okay. So, this is a matter of convention, and we are going to stick to this convention, that we are going to use delta y subscript t is equal to y subscript t plus 1 minus y subscript t. So, delta y t denotes the change in the value of y between periods t and t plus 1. So let us take an example. So suppose delta t is equal to 5. That means if we are starting from point t and we are taking t plus 1, then this gap yt plus 1 minus yt is equal to 5. And notice this can also be written as yt plus 1 is equal to yt plus 5. Okay. The value of y in a period gets added with this number 5 to get the value in the next period. So, that is what it basically means. In that same vein, when we say delta t is equal to 5, that means the same thing, that if we want to get the value of y in the next period, then we take the value of y in this period and add 5, and that will give me the value of y in the next period. This describes the dynamics of the variable, this variable y, and this is an example of our difference equation. So, this is a difference equation, delta yt is equal to 5, but this is also our difference equation because both these two things mean the same. Yt plus 1 is equal to yt plus 5. Yt plus 1 minus yt is equal to 5 is an example of a difference equation which is linear, right? Why is it linear? Because y's have a highest power of 1 and no two y's of different periods are being multiplied here. So, look at the power of the y's, there is no y square or y cube or even root over y, right. So, the only power of y's that is there is 1, and one can say that the 0 is also there because y to the power 0 is 1. So, this is the reason why we are saying it is a linear equation, and also it is the case that if we take the y's of two different periods, then they are not multiplied together. So, these conditions are being satisfied here, and so we are calling it a linear difference equation. The second comment about the typology of this difference equation is that it is a non-homogeneous difference equation. And the reason for that is that on the right hand side, that is here, where there are no y, what we have is a non-zero term 5. So, had we have a 0 here instead of 5, then we would have called this a homogeneous difference equation. But since we have a non-zero constant on the right hand side, so what is special about the right hand side here? The special thing about the right hand side here is that on the right hand side there are no y's, okay, and if there are no y's, we have a non-zero constant which makes this difference equation a non-homogeneous difference equation. Now, the third point, and this is very important, this difference equation is of first order. What is meant by first order? Since there is a first difference, that is delta yt, only a single period lag is there. So, look at this left hand side expression, it is yt plus 1 minus yt, and this is nothing but delta yt. Okay. So, there is just one period lag, and that means that this difference equation is a first order difference equation. For higher order difference equations, the time lags could be of 2 or more periods, right. So, we are going to talk about higher order difference equations as well after we have discussed the first order difference equations. But for the time being, let us try to summarize. This difference equation that we have here is a linear difference equation, it is a non-homogeneous difference equation, and it is a difference equation of the first order. Okay, here is an example of a difference equation which is linear and of first order but homogeneous. So, this is the new thing that is there in this difference equation, which was not there in the earlier one. And look at the form, it is saying that y t plus 1 is equal to half of y t. So, you can see that there is no constant term here, right. So, if I take y t to this side, right, then it will just become y t plus 1 minus half of y t is equal to 0. So, there is no constant term on the right hand side, and that allows us to conclude that this is a homogeneous difference equation. The other two criteria, that is linear and first order, those two criteria are being maintained like in the previous example. Now, actually this particular equation can be easily solved. Here, suppose we know y0. What is y0? Y0 is the value of this variable when time is 0. Time is 0, what is the speciality about that? Time is 0 is the point of origin from which time everything is starting, right. T0, then it could be T1, 2, like that. Time cannot be negative, okay. So, T0 is the point of origin. If I know the value of y at that point of time, that is, suppose it is y0, then actually I can do the following. From this equation I can immediately see that yt plus 1, that is y1, will be half of yt, that is in this case y0. So, I know y1. Similarly, y2 will be half of y1, but I already know y1. So, I substitute that here, and that gives me y2 as a function of y0. It is half whole square y0. Likewise, y3 will be half whole cube y0. So, you can see there is a pattern that is coming out from this series, and in general one can write yt, that is the value of y at period t, is equal to half to the power t multiplied by y0, and this is the solution of this difference equation. So, this method is the iterative method of finding yt, right, finding yt as a function of the constants and time, right. So, you can see here that on the right hand side there is no term involving yt or yt plus 1 or yt minus 1. Only thing we have is a constant y0, and here is also another constant half and time, right. So, this pattern that we are getting here will be called a solution. It will basically give me the value of y at any arbitrary point of time. So, if I am given the value of t, right, I can immediately tell you what is the value of yt. I will just put that t here, and I know what is y0. So, I will get the value of yt. But this iterative method cannot be applied everywhere. It is not a general method. Okay, here is the general method, solution of a first order difference equation. While solving a difference equation, our purpose is to find the time path of y. So, this is a new term I am using, time path, and this is denoted by yt, and we have seen that yt is also written as y subscript t. It defines the value of y for each value of small t. That is what I have just said, that if I am given the value of small t from the solution, I can give the value of the y, that is the variable. Such a time path is free from any difference expression. So, it does not involve this kind of expression delta yt. It is consistent with the given difference equation. So, let us take this example. This solution that we got here is consistent with this given difference equation. Okay, you can just check that. So, if suppose I am to find out what is y1, y1 will be half of y0, and that is consistent with this general form, right. Here also y1 will be half of y0. And the initial conditions. What is meant by the initial conditions? The initial conditions is, this is an example of an initial condition, that at t is equal to 0, I know what is the value of y. It is given by y0. So, that is an initial condition. So, the time path or the solution of the difference equation has to satisfy these criteria. Firstly, it should not include an expression like this, delta yt. It is consistent with the difference equation that is given to us, and thirdly, it should satisfy the initial condition. Okay, suppose we want to solve a general first order difference equation of this form: yt plus 1 plus a yt is equal to c, where a and c are two constants. So, these are given to us. We know the value of a, we know the value of c, and the difference equation is this: yt plus 1 plus a yt is equal to c. All right, we have to solve this. And as you can see, it is quite general, this expression, because we are having a non-homogeneous difference equation, right. If we put c is equal to 0, it becomes a homogeneous difference equation, but that will be a special case. And the lag is just 1, right. So, that means it is a first order difference equation and it is linear. Okay. Now, the solution of this difference equation will consist of two parts. The first one is called the yp, or the particular integral. Sometimes it is also written as pi. And the second part is yc, and it is called the complementary function, and it is denoted sometimes as cf. So, the solution will be a combination, a summation of these two things, yp and yc. The particular integral is what? The particular integral is any solution of the complete non-homogeneous equation. Okay. So, this is given to us, the particular integral is any solution to this equation. It represents the intertemporal equilibrium value of y. Intertemporal equilibrium value of y. Since y, that this particular integral is going to satisfy this, so we can say that this solution that we are talking about is an equilibrium value. What is the intertemporalness of this? That we are going to find out shortly. The second part, that is the CF, the complementary function, is the general solution of the reduced equation, this yt plus 1 plus a multiplied by yt is equal to 0. So, notice the difference between these two. Here the constant term has been got rid of. So, it is a homogeneous equation now. So, the CF, or the complementary function, is the general solution to this homogeneous part of the difference equation. Now, what does the CF denote? It denotes the deviation of the actual value of y from the equilibrium value. And what is the equilibrium value? That is yp at any period. Equilibrium, not only equilibrium, it is the intertemporal equilibrium value, right. Yp is the intertemporal equilibrium value of y. The general solution is the sum of yp and yc. This we have just mentioned. The solution is summation of these two parts, yp and yc. It is called so because of the presence of the arbitrary constant. We are going to talk about that in the general solution, an arbitrary constant will be there. And the initial condition, we have talked about initial conditions before, that will help us obtain the definite solution. Okay, at this point of time, it might seem a little bit abstract, a little bit vague what we are talking about. So, let us try to solve a particular equation and try to see concretely what we are trying to say. Okay, for this difference equation, which is the general form, this is the general form, let us try to find out the complementary function and the particular integral and try to see what does the solution look like. We start with a trial solution. So, we are trying to find the complementary function of this equation. We try a solution of this form a b to the power t, where a and b are constants. Now, why did we take this particular form? This is basically coming from this solution that we have just done. So, here you can see there is a constant term here, and then it has been raised to the power t, and there is a constant term multiplied with that, right. So, that is the form that we are using here to get the complementary function. Now, if y t is equal to this a b to the power t, then y t plus 1 will be a b to the power t plus 1, right. So, I know y t, I know y t plus 1, and then I will substitute these in this homogeneous equation. Now, if I do that, then I get this, and I can take a b to the power t common on the left hand side. So, within the brackets I will get b plus a, and whole thing will be equal to 0. Now, a b to the power t is not equal to 0. I am assuming b and t, they are not 0. So, this will not be equal to 0. So, the other possibility is that this part is 0, b plus a is equal to 0, and that gives me the solution for b. Remember, b was something which we do not know. I just assume that it is a constant, non-zero constant. So, I know b now is equal to minus a. So, that the complementary function is y c is equal to a multiplied by minus a, that is minus small a to the power t. Now, mind you, still we do not know the value of capital A, right. This was an arbitrary constant. We have to get a hold of that at a later point of time. Now, pi is still left out, that is particular integral. Let us suppose it is given by y p, and we try a simple solution, right. Remember, particular integral is any solution which solves the given difference equation. So, I take the simplest possible solution that can happen, that I take y p is equal to k is a constant. Okay. Now, if k is constant, then y t plus 1 and y t, both of them will be equal to k, because k does not change with respect to time. And I substitute these things in this equation. So, what do I get? K plus a k is equal to c, right. So, that means that k is equal to c divided by 1 plus a. So, this is the solution that I am getting here of the particular integral, but mind you, this can be a solution, this can be a particular integral if the denominator is not 0, c divided by 1 plus a cannot be 0, that means a cannot be equal to minus 1. Okay. So, this is something which we have to keep in mind. Now, putting all this together, I get the general solution. This is the general solution. Y t is a summation of the particular integral and the complementary function. This was the complementary function, a multiplied by small a minus of small a to the power t plus c divided by 1 plus a. This is the general solution. Now, we do not know the capital A. To find that out, we need an initial condition. So, suppose the initial condition is this, that at t is equal to 0, y t is equal to y 0. So, I use this information in this equation here. So, if I do that, think about what will be the outcome of that. On the left hand side, I am going to get y 0, I am putting t is equal to 0, alright. So, on the left hand side, I am going to get y 0 and then equal to this will become 1, right. This becomes 1 because minus a to the power 0 is 1. So, this becomes capital A plus c divided by 1 plus a. Y 0 is equal to a plus c divided by 1 plus small a, and that gives me the value of capital A. Okay. So, the arbitrary constant has been gotten rid of, and so I substitute this capital A back to the general solution, and I get this expression y t is equal to y 0 minus c divided by 1 plus a. This was the a, all right, multiplied by minus a to the power t plus the particular integral, which was c divided by 1 plus a. The only thing here to note, and which is a point of discomfort, is that this solution is valid if a is not equal to minus 1. But obviously, we cannot a priori say that a is not equal to minus 1. So, we have to cover that case as well. What happens if a is equal to minus 1? If a is equal to minus 1, then our particular integral has to be different. So, instead of yp is equal to k that we assumed earlier, here we are taking this particular trial solution, yp is equal to k multiplied by t. So, it is a function of t now, a little bit more complicated than what we had before, and let us try out whether this works out or not. So, this yp, which is basically equal to yt, we substitute that here, right, and if we do so, then what we are going to get, instead of yt plus 1, I write k multiplied by t plus 1 plus a multiplied by kt is equal to small c, and from the left hand side I can take k common, and within the brackets I have a t plus t plus 1, right. From here I will get a t, then t plus 1. On the right hand side I have only small c. But if a is equal to minus 1, right, here I can write minus 1, then minus t and plus t will get cancelled. So, I am just left with k is equal to c, all right. So, this is the solution of the particular integral. It is yp is equal to c multiplied by t. So, the general solution in this case is yt is equal to the cf plus the pi. Cf is a multiplied by minus a to the power t plus c multiplied by t, the particular integral. But again I have to get rid of capital A. So, I again use the initial condition. If I do so, therefore, I will get if I put t is equal to 0, this part vanishes. So, capital A will be equal to y 0. Further, since a is equal to minus 1, so this part just becomes 1, right. So, minus a to the power t becomes 1. So, the solution actually is a very simple looking solution. It is yt is equal to y 0, right. Y 0 is coming from this a part, complementary function, plus the particular integral, which is ct. Okay. So, this is the solution here in the case where small a is equal to minus 1. So, actually you have two kinds of solution. This is the solution if you have a not equal to minus 1, and this is the solution where a is equal to minus 1. Okay, here we are having an example. Solve the first order difference equation, this yt plus 1 plus 3 yt is equal to 4. The initial condition is given, that the y0 is equal to 4. All right. First, let us try to find out the particular integral. So, yp, that is the particular integral, let us suppose it is constant k. So, we substitute that here, k is not dependent on time, right. So, yt plus 1 and yt, both of them are equal to k. So, therefore, I have k plus 3k is equal to 4 or k is equal to 1. So, this is the particular integral. As far as the CF is concerned, I am assuming yc is equal to a b to the power t, right, and that I substitute back to this equation. On the right hand side, I do not take 4, I take 0, right, the homogeneous equation, and thus we get a b to the power t plus 1 plus 3 a b to the power t is equal to 0, and that simplifies to b plus 3 is equal to 0 or b is equal to minus 3. Therefore, the general solution is this: yt is equal to the CF plus the pi a multiplied by minus 3 to the power t plus 1, and I have to use the initial condition, which was y0 is equal to 4, right. That is, if you take t is equal to 0, then on the right hand side you are going to get a multiplied by 1, because minus 3 to the power 0 is 1, plus 1, that is a plus 1, and on the left hand side y0 is equal to 4, that is 4. So, from here I get a is equal to 3. So, I get the solution to be this: yt is equal to 3 multiplied by minus 3 to the power t plus 1. And if you have noticed what was the general template of the solution of first order difference equation, it was this, right, and this actually matches with this and these two are tallying with each other, because in this case this particular example that we have, it is yt plus 1 plus 3 yt is equal to 4, that is the form that is given to us, and y0 is equal to 4, right. So, in this case a is equal to 3 and c is equal to 4. Okay. So, a plus 1 is 3 plus 1, so that will be 4, and c is equal to 4. So, 4 by 4 is equal to 1, and therefore, you have after that 4 minus 1 multiplied by minus a is equal to minus 3 t plus c divided by 1 plus a, that we have just seen it is 1, because 4 divided by 1 plus 3. So, this is nothing but 3 minus 3 t plus 1. So, this is the yt predicted by this template, and that is exactly what we have found out by our more elaborate method. Okay. What about dynamic stability of the equilibrium? Now, when we say dynamic stability of equilibrium, let us try to define what we mean by dynamic stability. Now, in this time path, that is yt is equal to yp plus yc, right. This is what we have seen before. Yp is the particular integral, it is the intertemporal equilibrium value. Okay. So, irrespective of the time, this gives me the equilibrium value, okay, this part. The equilibrium is dynamically stable, it should be dynamically stable if, irrespective of the initial condition, the time path this converges to the equilibrium. Okay. So, yt, if it converges to yp, irrespective of where we are starting from, that is where the y0 is, if yt converges to yp, then we say that the equilibrium is dynamically stable. Thus, whether the equilibrium is stable or not depends on if the complementary function, that is the other part yc, which we know is equal to a b to the power t, goes to 0 or not as t goes to infinity, right. So, if this part slowly gradually drops out, it dies down, then yt converges to yp, right, and in that case we are saying that the equilibrium is stable. Now, the value of b assumes importance in this context, since the term b to the power t determines the nature of yc as t goes to infinity. Now, that is obvious. You see, yc is equal to a b to the power t. T is going to infinity, it is becoming larger and larger. So, what is the value of b? That will determine whether yc slowly drops out or not, right. So, the value of small b, that constant, is of critical importance. Now, there can be several qualitatively different values of b as explained below. Okay. So, different types of b that can occur. So, this is called the typology of b. There can be 7 possible regions, from which b can take its value. I am just going to introduce this and maybe we can discuss it in more detail in the next lecture. So, b can be greater than 1. So, think about a straight line, the real number line. Here you have plus 1, here you have minus 1, plus infinity, minus infinity. So, value of b can be here, right, more than 1. It can be exactly equal to 1. It can be between 0 and 1. It can be at exactly 0. It can be between 0 and minus 1. It can be equal to minus 1, or it could be less than minus 1. So, these are the 7 distinct possibilities of b, and each of them might give us different kinds of stability, right, and that is what I have commented in the third column here. I shall take it up in the next lecture, and there I can carry it forward further. And so, let me stop here for the time being. I shall see you in the next lecture. Thank you.